10 years have passed since Interstellar was released on the big screens. Since then, in the minds of the vast majority of people, the movie continues to be positioned as the author's project of Christopher Nolan, and Kip Thorne is mentioned only in passing, as some kind of scientific advisor. Let it be known that it is Thorne who is the author of the idea. But who is he anyway, some will ask. Kip Thorne is, without exaggeration, a modern genius in the field of gravitational theory, astrophysics, and quantum measurement theory. After all, he is one of the world's foremost experts on the general theory of relativity, as well as a Nobel Prize winner in physics. Back in 2005, he and his ex-wife conceived Interstellar as a movie that would show mass audiences the wonders that the real laws of physics give us. Things that are true, or quite likely to be true, from the standpoint of current knowledge of our universe. A movie that would inspire a wide audience to learn about science, or even get into science. After the release of Interstellar, Thorne published an entire book where he laid out the basic ideas on which the picture is based, fully supporting them with scientific data. And guess what? Keyboard warriors on YouTube and sometimes even well-respected Twitter popularizers like Neil Tyson, before loudly flapping their tongues, did not even bother to read it. It begs a very reasonable question. Where is at least one YouTube video that properly explains Thorne's ideas in the movie? After reading this book, you will be blown away by how differently the movie is perceived. Do you know what the director's cut is? This is the director's version of Kip. The Science of Interstellar is how Thorne sees what's going on in the movie and his thoughts on it. If you have any qualms about the scientificity of a particular moment in the movie, there is almost certainly an educated explanation in the book. But most importantly, it describes a lot of moments that went under the knife because it is impossible to create a massively profitable 10-hour blockbuster packed with scientific terminology. Everywhere you turn, you have to simplify and reduce. And I have to do the same. I'd love to talk for hours about all the ideas in the book, but there's hardly a viewer for that. And the whole video is quite difficult to understand because the narrative is not burdened with platitudes. Therefore, if you are seriously interested in popular astrophysics, the book can always be read in electronic version. To begin with, you should know that before filming, Thorne proposed several rules limiting the director's flight of fancy to the generally accepted laws of physics and the most reliable hypotheses about phenomena in the universe. However, whatever the weight of Kip Thorne in the camp of physics, Hollywood is not his territory. Nolan, one of the most influential directors of the 21st century, a director with acclaim, and objectively, he has the right to do so. Therefore, in the movie, the maestro could show everything that he only wants to. At times, he did. Here are his words to Kip Thorne. Kip, if you don't like the way I handled the science in the movie, you don't have to defend me. Those words made Thorne feel bad, but in the end, he was quite happy with the way Nolan followed the rules, with a few caveats which I'll tell you about in the process. To begin with, Interstellar has no beginning or end. Few people have noticed this, but the first and last scenes of the movie are identical. We are shown bookshelves, Old Murph, and Cooper's downfall. And here, we are also shown Cooper's fall, the Old Murph, and the bookshelves. Cooper's fall into Gargantua in the finale set in motion all the events of the movie, starting from the first frames, and all those same events ultimately led to Cooper falling into Gargantua. Thus, the story begins with an ending and ends with a beginning. The movie is looped. Beautiful, sure, but the true poetry and meaning lie deeper. People believe that the curvature of space near a black hole is caused by a huge amount of matter, tightly compressed into a single point. However, this is not the case. Black holes do not contain any matter. In fact, the space-time of a black hole is warped by the monstrous energy of its curvature. If you think this statement is looped, you're not wrong. It takes a lot of energy to bend a bow before firing a shot. To bend space-time, energy requires a bit more. And just as the energy of bending is stored in a bent bow, the energy of warping is stored in the warped space-time of a black hole. And this energy is so great, it causes the warp itself. Warp generates warp in a non-linear looped fashion. It's quite elegant. We intuitively know that an object in the universe cannot have a diameter greater than the length of its circumference. It can't? It can't. But if you stretch a measuring tape from one edge of a black hole to the other, it turns out that it can. This is a consequence of the infinite stretching of space inside. But since space is inseparable from time, time is also infinitely stretched. Therefore, an outside observer will never see an object cross the event horizon. That's why it's called the event horizon. And based on the equations of the black hole, space-time flows as if downward. So, for you to understand, having fallen through the event horizon of a supermassive black hole, the point where your death will come is not just a point in space, it's a point in time. It's a point in the future, and it's as inevitable as tomorrow. And this is not a beautiful metaphor. The downward flow of time is the reason why getting out of a black hole is the same as going into the past at the moment when you have not yet crossed the event horizon, because no matter which way you go on Sunday, you will always arrive on Monday anyway. Once you fly your spaceship over the event horizon, no matter where you go, you will arrive at the singularity. It is only to an outside observer that your time is infinitely stretched out, but to your personality, it is quite finite. Cooper, on the other hand, not only managed to transmit data from the inside, but also to get out. In what way? The answer is on Wikipedia. And the answer is a naked singularity. Black holes. Naked singularities. Physicists are all right with the names. They are not boring guys. But getting to the point, think of the gravitational anomalies of the movie. They worry Professor Brand for two reasons. If he understands their nature, he can figure out how to control them, and this will help NASA evacuate large colonies of people from the dying Earth. In the Kip version, if the Earth's gravity becomes 1,000 times less than its normal value, even if only for 1 hour, rocket engines of minimal size with minimal fuel will be able to launch into space the huge centrifuges with colonies that are shown in the beginning and end of the movie. With normal gravity, this would be absolutely impossible. The native Earth, of course, would not fare well from such manipulations. The key to understanding and controlling anomalies is an equation that the professor has written on his blackboard. This equation contains known parameters such as functions, constants, and hyperspace fields. And it's not just meaningless gibberish, it's complicated math that's far more advanced than it looks. In short, to find these unknown parameters from the equation, it is necessary to learn the laws of quantum gravity, about which we still know almost nothing. Theoretically, the answer lies in the core of black holes, in the singularity. But you see, here's the thing. Singularities are hidden from our observation beyond the event horizon, so we can't see and study the compression of an object to infinite density. But really, who knows? We don't have a serious theoretical basis that prohibits the existence of naked singularities, that is, singularities without an event horizon. Purely hypothetically, if the hole were to spin fast enough, the singularity would form a ring with zero thickness but non-zero radius. Again, this is hard to imagine. The singularity itself is a point with zero radius, but the ring that would have to form if it rotates fast enough would have a radius that is quite non-zero. Due to such rotation, two event horizons are formed, external and internal, and the faster the singularity rotates, the closer they converge, until the event horizons disperse, exposing the singularity. In other words, you get a black hole without an event horizon, a black hole whose insides we can see. What would it look like? Probably like this. Cooper could fly into such a singularity, collect the data, and return without any consequences. Except there's no naked singularity in Interstellar. I have no idea what imbecile wrote that on Wikipedia. Speaking of the book, there is indeed a passage in the book about the naked singularity, but it only mentions it in passing. You know what else is in the book? Wikipedia articles should always be read with a degree of skepticism. I estimate that about 10% of the statements on Wikipedia relating to the fields of knowledge in which I specialize are incorrect or misleading. Kip Thorne. Gargantua is, without a doubt, the gem of the movie. No one has ever given people such an accurate and high-budget visualization of a black hole until now. When I was a kid, the illustrations of black holes in astronomy books from the local library, you know what they looked like? They all looked like this: a 2D flat black disk in 3D space. As an adult, I had already forgotten to dream of seeing how these space monsters looked in reality. And then, Suddenly, an amazing, unimaginable movie illustration. I was shaking at that moment in the theater. It was this image of a black hole from the movie that became firmly embedded in popular culture. Now children all over the world have ideas of what a black hole should really look like, because this is what Gargantua would look like in reality, with a few exceptions. A mass of 100 million solar masses was chosen for the black hole shown. The diameter of any black hole with a mass of 100 million solar masses is equal to the diameter of Earth's orbit around the Sun. So if you were admiring a sunset right now and the Sun was suddenly replaced by Gargantua, you would find the event horizon literally right under your nose. That's how huge Gargantua is. That's far more than enough mass to keep the planet Miller, which orbits critically close to the hole, from being torn apart by tidal forces. Yes, critically close indeed. When Christopher Nolan told Kip Thorne that the time dilation on Miller's planet should equal 7 Earth years per hour, Thorne was absolutely floored and went off to do the calculations. For time to slow down that much without the planet plunging into the black hole, the hole had to be spinning, and spinning damn fast. And for spinning black holes, there's a limit, which I assure you already know. When a black hole spins, it drags everything on its orbit along with it, but the speed of these objects cannot exceed the speed of light, according to the calculations. To meet Nolan's request, Gargantua had to spin at just 1/100th trillion below the ultimate limit. In other words, an object in its orbit would have to complete a full circle around the hole in 1 hour, a nearly billion-kilometer trip. And 1 billion kilometers per hour is almost the speed of light. You see, there's a mechanism that prevents black holes from spinning faster than the limit. As the spin nears the threshold, it becomes increasingly difficult for the black hole to capture objects orbiting in the same direction as its spin, objects that would further increase its rational speed. However, the black hole has no problem at all capturing objects moving in the opposite direction, which instead slows it down. So, as the black hole easily slows itself when its speed approaches the limit, apparently this balance is quite stable, and in most cases, a black hole's rotational speed doesn't exceed 0.998 of the limit. Still, theoretically, the speed Nolan needed is possible. Theoretically, as I mentioned when discussing a naked singularity, speeds beyond the limit might exist, where the event horizon would dissipate, exposing the singularity. Now, what do you think happens to space near a black hole spinning that fast? People without imagination couldn't care less about space. It's far away, untouchable, they say. But a person with a quicksilver, dynamic mind only needs to close their eyes to imagine that near such a spinning black hole. It's not just dust and gas swirling, it's space-time itself. And there's no unseeing that. On the left side of the diagram, space is moving toward us, while on the right, it's moving away. Because of this, the black hole's shadow looks flattened on the left, and the starry sky looks oddly twisted. Moreover, this space vortex pushes the accretion disk away from the shadow on the left and brings it closer on the right, making the disk look skewed. And if I haven't mentioned the Doppler effect, which would make the disk appear bright blue on the left and dim red on the right. Nolan worried this would confuse viewers, so he decided to slow Gargantua down to 0.6 of the speed limit, making all these weird effects less noticeable. So according to the script, the black hole spins near the limit, but what we see on screen is a simulation at 0.6 of the maximum speed. Fair enough, but how do you even reach a black hole in another galaxy? In Kip's version, while reviewing data from the LIGO detector over the past 2 years, Professor Brand and his team discovered gravitational waves coming from a neutron star orbiting a black hole, and all this somewhere around Saturn's orbit. A black hole near a neutron star, both orbiting Saturn? Scratching his head, Brand realized this was impossible, because if it were true, he wouldn't have had time to scratch his head. And yet, the waves clearly came from somewhere near the 6th planet. The professor could only think of one explanation. The waves were coming from a wormhole orbiting Saturn, with the sources of the waves, the black hole and neutron star, on the other side of the wormhole. But even without gravitational waves, the sheer amount of complicated material in the movie was already overwhelming. So, Nolan looked for ways to simplify the script. Gravitational waves were the first to go. So, the whole story was shortened. Wormholes weren't fiction. Their existence follows directly from the equations of general relativity. The thing is, we just don't know yet if they really exist. No big deal. Gravitational waves, for example, were also a theoretical prediction, and when the movie came out, their existence still hadn't been experimentally proven. A few years later, they were detected, using the very LIGO detector Kip Thorne helped develop, which earned him the Nobel Prize. So who knows, maybe wormholes are next in line to be discovered. Since you're still watching this video, you're probably familiar with the concept of quantum entanglement, the spooky action at a distance, as Einstein called it. So why bring this up? There's a hypothesis that explains the instantaneous connection between entangled particles by suggesting that they are connected through wormholes. I remember how everyone snickered at that scene in the movie, where Romilly demonstrates a wormhole's function with a piece of paper and pencil. So simplistic, like a kindergarten lesson, they said. Well, in his book, Thorne offers an explanation for the intellectuals. Research in quantum gravity suggests that our universe is a membrane, a brain, existing in bulk, or in other words, multidimensional hyperspace. The bulk is that very fifth dimension they keep droning on about throughout the film. Think of the apple's skin as our universe, the brain, and its flesh as the bulk. Many people wonder, if space curves under the influence of massive objects, where does it curve to? The answer? Into the bulk. We can imagine several strategies for constructing a transversible wormhole, one through which Cooper and his team could travel millions of light years away from home. I'll just focus on one. To use this strategy, we'd have to shrink ourselves down from the ordinary world to the atomic scale, then to the nucleus of an atom, and then dive even deeper by 20 orders of the magnitude to 10 to the negative 33 power centimeters. At larger, familiar scales, space appears completely smooth, with a defined but tiny curvature. However, as we approach the scale of 10 to the negative 32 centimeters, we start to see space twisting, first a little, then more and more violently. By the time your microscope's field of view shrinks to 10 to the negative 33 centimeters, space would transform into the froth of quantum foam, a hypothetical network of wormholes that pop in and out of existence according to the still poorly understood laws of quantum gravity. It's tempting to imagine an advanced civilization that managed to reach the quantum foam, found a wormhole in it, and tried to capture it and expand it to a macroscopic, transversible size. If the civilization were advanced enough, they'd succeed in a certain percentage of cases. To keep the wormholes from instantly collapsing, this ultra-advanced civilization would need to fill it with a negative mass matter, something we can already produce in small amounts in laboratories today. But Thorne doesn't make any guarantees. Scientists still aren't sure if quantum foam even exists. There's now a reason to believe that the laws of quantum gravity could suppress the foam, preventing it from foaming in the first place. But if quantum foam does exist, there's a chance that, through some natural process, a few of these microscopic wormholes might spontaneously expand, perhaps to human scale or even larger. I'd like to see that. Then again, we already know that black holes, for instance, form naturally when a certain amount of matter collapses under gravity. But what exactly would have to happen for a tunnel through hyperspace to form? That's still an open question. Nevertheless, it's been known for quite a while that Einstein's equations allow for the existence of wormholes with different shapes and properties. There's everything, perfectly spherical and transversible wormholes, and even ones that don't contain gravitational matter. So many people mistakenly claim that wormholes must have a mass of black holes. No, not necessarily. Some calculations even suggest that a transversible wormhole wouldn't require exotic matter at all. In his book, Kip Thorne spends a lot of time speculating about the properties of wormholes. He admits that the natural formation of transversible wormholes in the universe is extremely unlikely. Even for a super advanced civilization, creating such an object would be a task with an asterisk. But in Interstellar, the civilization that placed the wormhole near Saturn is not just technologically advanced, they are eons ahead of us. I need to comment on something right away.
Don't you get it yet, Tars? They're not beings. They're us.
There's not a single moment in the film that could serve as a premise for such a conclusion. Not a single hint. In his book, Kip Thorne writes that if there are any beings in hyperspace, they certainly cannot be made of the same matter and atomic structures as us. Atoms can only exist in 3 spatial dimensions, not 4. The same goes for subatomic particles, electric and magnetic fields, and the forces that hold atomic nuclei together. In Thorne's book, there's an entire chapter dedicated to the beings of the bulk and how they might interact with our universe, but nowhere does it say that they're people from the future. At the end of the chapter, he merely points out that the idea to make the inhabitants of hyperspace our descendants belonged to Nolan. Commentary over. Let's move on. So, why does the wormhole in the movie look the way it does? Once again, its visual characteristics weren't just pulled out of thin air. They're based on Thorne's equations and calculations, which were translated into computer code and used to generate high-quality IMAX images. But here's the thing, Nolan didn't chuck half the equations out the window during post-production and chose a far more abstract interpretation of the wormhole's interior, simply because with the given parameters, the trip through it would have been too fast, and in Nolan's opinion, boring. Annoying? Maybe a little, but at least its exterior looks as it should. It's the same story as with the black hole. Have you ever seen how wormholes were portrayed before? In books, movies, and popular culture in general, wormholes looked something like this. What a disgrace. Besides, using Thorne's equations and Nolan's chosen properties of the wormhole, we can still see what the trip would have looked like in reality. Not in IMAX quality, of course, but we can live with that. I've already mentioned the size of the black hole in Interstellar. Its event horizon is comparable to the diameter of Earth's orbit around the Sun, and many viewers noticed that Cooper's crew spent 2 full years in hibernation capsules traveling from Earth to Saturn, yet they zoomed around the supermassive Gargantua like it was their backyard. There's a clear scientific explanation for this too. The black hole's gravity accelerates objects to relativistic speeds. But here comes another problem. As the spaceship falls toward the black hole, it picks up tremendous speed, and it somehow has to slow down. Based on the calculations, for Cooper to match the velocity of the first planet, Miller's planet, which orbits at 55% the speed of light, the ship would have to lose almost 100,000 kilometers per second to align with the planet's speed for a close approach. Rocket engines capable of that don't exist and aren't expected to exist even in the most optimistic, far-off future. The solution? A gravitational slingshot. NASA has used the gravitational fields of planets many times to save fuel and give spacecraft a speed boost. The faster an object spins and the greater its mass, the more speed, or braking force, you can gain using its gravitational field. Over hundreds of millions of years, supermassive black holes like Gargantua have accumulated countless stars and smaller black holes around them, which could be used for gravitational slingshot maneuvers. These maneuvers aren't shown or discussed in Interstellar because, let's face it, the movie is already pushing 3 hours. Still, a neutron star wouldn't work for this. Despite its incredible density, a neutron star can't be larger than 20 to 30 kilometers in diameter. Because of the sharp gravitational gradients due to its small size, any spacecraft approaching would simply be torn apart by tidal forces. Thorne suggested to Nolan that, for scientific accuracy, they use a black hole at least 10,000 kilometers in diameter instead. But Chris went with the neutron star anyway, fearing the audience would get confused if the film featured more than one black hole. Once Nolan understood that powerful gravitational maneuvers were necessary for navigating near Gargantua, he had Cooper briefly mention it, at the expense of scientific accuracy. But hey, at least he mentioned it. After the gravitational slingshot, the crew ends up on their way to the first planet of their journey. The time dilation on Miller's planet is 60,000 times stronger than on Earth. At such a close orbit, the planet experiences monstrous tidal forces so extreme that they should simply rip the planet to shreds. And that's not far from the truth. They almost do. Miller's planet gets severely stretched toward and away from the black hole. If the planet were orbiting Gargantua with any radial motion, friction and its mantle would heat it to a fiery red glow. The conclusion? The planet must always face Gargantua with the same side. And here is where your mind gets blown. Einstein's laws tell us that, viewed from afar, Miller's planet orbits Gargantua along a billion-kilometer path, completing one revolution, according to Thorne's refined calculations, in 1 hour and 42 minutes. Do you realize what this means? Cooper's team, while on the planet itself, measuring its rotational speed due to the time dilation, would get a value that's 60,000 times smaller. Let me repeat that so it sinks in. If you're watching Miller's planet from afar through your telescope, it completes an orbit around the black hole in 1 hour and 42 minutes. That's absurdly fast. A billion kilometers in 1 hour and 42 minutes, but time on the planet itself is slowed down. Remember? 1 hour on the surface equals 7 years in undistorted space-time. This means that while a distant observer sees the planet complete its orbit around Gargantua in 1 hour and 42 minutes, for someone on the planet, one orbit takes 60,000 times less time. Cooper's team, standing on the planet, would measure one orbit around the black hole as taking just 0.1 seconds. Think about that. If you were watching Miller's planet through a super powerful telescope, it would appear as if, despite its blistering orbital speed, time on its surface has almost frozen. But for someone on the planet, time feels perfectly normal, second by second. Thus, while distant observers see the planet orbit Gargantua in 1 hour and 42 minutes, for someone on the planet itself, it completes 10 orbits per second. Let that sink in. 10 orbits per second around a supermassive black hole, whose diameter alone matches Earth's orbit around the Sun. That's 10 billion kilometers per second, while the speed of light is 33,000 times less. So does this mean the planet moves faster than light? No, not at all. The explanation lies in that space-time vortex created by Gargantua's rapid spin. Relative to the twisted space and time where the planet resides, its speed is still below the speed of light. People I know will say, "What the fuck? What is this critical orbit nonsense?" Judging by the movie's frames, Miller's planet looks like it's hellishly far from Gargantua, and you'd be right. Do you know where Miller's planet should be, given all its properties relative to the black hole? If you stood at a particular spot on the planet and looked up at the sky, the event horizon would occupy your entire field of view, with its accretion disk setting just outside the planet's orbit. However, Nolan saved such grandiose visuals for the editing, shrinking the angular size of the black hole when viewed from Miller's planet. Thorne fully supported him on this. And then came the moment when every viewer even remotely familiar with astrophysics held their breath. Cooper falls into Gargantua. What would the esteemed physicist show us inside a black hole? I remember craning my neck in the theater, greedily absorbing every single frame. This scene really deserves to be analyzed second by second. But first, let's sort something out. An ancient rotating black hole contains what's known as a soft singularity. An old black hole with a soft singularity. What does that even mean? Back in 1985, when Carl Sagan wanted to send the protagonist of his novel to Vega via a black hole, Kip Thorne told him, no, she'd die inside the black hole. A merciless singularity would tear her apart. Instead, Thorne proposed a journey through a wormhole. Sagan agreed, and that's how wormholes made their way into books, movies, and pop culture. Thorne too left his mark. But in 2013, Kip Thorne supported Christopher Nolan's desire to send Cooper into Gargantua. So what changed in a quarter of a century? In 1985, physicists believed that the center of all black holes harbored chaotic and disgustive BKL singularities. Anything that fell into a black hole would be obliterated by the singularity's stretches and compressions. It was a reasonable assumption, but they were wrong. Over the next 25 years, 2 additional types of singularities were mathematically discovered inside black holes. 2 soft singularities, soft enough that Cooper, falling into one, would have a chance to survive. So now, for science fiction, survival inside a black hole is a perfectly acceptable possibility. But let me clarify something about singularities. I said there are 3 types, but almost everyone imagines a 4th type. Most people still think of a black hole's singularity as a shrinking point in space where matter becomes infinitely dense. This perception is reflected in those familiar illustrations I've shown before. The truth is, such singularities probably don't exist. They're far too unstable. To form such a singularity inside a black hole, you'd need fine-tuning. And if anything disturbs it even slightly, say something falls into the black hole, it would transform dramatically. Into what? Into a stable BKL singularity. BKL singularities are chaotically violent and devilishly dangerous. Falling toward one, the space around you would start stretching and compressing wildly, along with you. The amplitude would grow and grow. As it approached infinity, your flesh would be ripped apart, then your atoms, and eventually, the very particles of your body would be shredded beyond recognition. All of this follows directly from general relativity. What happens to your atomic remains? Only the laws of quantum gravity know. And boy, do we need quantum gravity laws. Now, if you fall into a rotating black hole like Gargantua, all sorts of stuff will inevitably fall after you. Gas, dust, light, gravitational waves, and so on. To an outside observer, all this matter would seem to be falling into the black hole over millions or billions of years. But from your perspective, inside the black hole, it would take just seconds, if not less, because of the extreme time dilation. Everything would come crashing down behind you at near light speeds, creating immense tidal forces that warp space itself. These tidal forces would grow infinitely strong, creating a plunging singularity. It's considered soft because it arrives so quickly, and while the tidal forces would eventually approach infinity, the overall stretching and compression of your body would remain finite. Confused? Let me simplify. Imagine someone drops a train car on me for just a fraction of a second. Despite the crushing weight, my body would only deform slightly because the fall is so brief. So yes, you'd have a slim, very slim chance of surviving entry into a plunging singularity. Thus, falling into a black hole, you'd encounter the deadly BKL singularity. Above you, the theoretically less deadly plunging singularity comes hurtling down. You'd think it couldn't get any worse, but oh, it can always get worse. At the end of 2012, yet another singularity was discovered inside black holes, and it's so obvious that Thorne himself wondered why no one had found it earlier. Its origin lies in the matter that fell into the black hole before you. A small part of that matter would scatter upward toward you, warped by the curvature of space-time, forming a thin layer resembling a shock wave. The gravity of this layer generates tidal forces that grow infinitely strong, creating an outgoing singularity. And it's soft for the same reasons as the plunging singularity. As black holes age and matter keeps falling into them, both the outgoing and plunging singularities grow. When Thorne told Nolan about these singularities, Nolan immediately decided which one Cooper would encounter: the outgoing singularity. That's what Romilly refers to as interstellar. And that's exactly what we see on screen, matter scattering toward Cooper. But why did Nolan choose only the outgoing singularity? Wouldn't it have been cooler to show both? Think again about the plunging singularity. What is it? It's matter that's been falling in for millions of years. Hypothetically, if you were to fall into a black hole, you could witness the heat death of the universe, something that, for everyone else, would happen septectillion years from now, while for you, it might feel like just a few seconds. Imagine the vastness of space. Absolute silence and utter loneliness. You, an insignificantly small human, are being pulled into the cosmic abyss, a monstrous entity, embodying the most terrifying force in the universe: total darkness. You hear nothing but the sound of your breath inside the spacesuit, the sound of your breathing and the thoughts whispering to you that the people you once knew are dead. And it's not even about your family and friends. It's about people. Humankind as a whole, and they've been dead for so long there's no trace of Earth, no solar system, no stars in the night sky. So many people have passed that after the death of humanity, countless civilizations across the universe have been born, lived, and gone extinct. And yet here you are, the last living and, it seems, tragically conscious being. In the entire history of existence, no one has ever been and ever will be a greater orphan. As for your death, it will come in a matter of seconds, just a heartbeat before time itself ends in the universe. Had the script gone this way, no one would have helped Cooper reunite with his daughter, because even Nolan himself said a firm no to time travel. But even this moment has a strict scientific explanation in Kip Thorne's version. To keep it brief, if you fall into a black hole at a high enough velocity, the plunging singularity might not catch up with you. For the same reason, thanks to Cooper's accelerated descent into Gargantua, he doesn't experience an extreme time shift. In other words, for him, time flows almost the same as it does for the external universe. This is why Brand doesn't age relative to Cooper by the end of the movie. Let's return to the analysis of the frames inside the black hole. Looking downward, Cooper sees light from objects that fell into Gargantua before him and are still falling. These objects don't need to emit light themselves. Cooper sees them because they are reflecting light from Gargantua's accretion disk. Most of these objects are interstellar dust, which explains why Cooper sees a haze. Additionally, he can obviously overtake objects falling slower than he is. This explains the white specks that hit the Ranger and bounce off of it. What do we see next? The Ranger encounters growing tidal forces. Cooper's body experiences stretching and compression. Yes, it's painful. At the last moment, Cooper ejects himself, and the tidal forces tear the Ranger apart. And then we see the rapidly approaching outgoing singularity. There it is, in all its glory. But what is it? Many, no, everyone was bewildered by the fact that Cooper, after falling into a black hole, ended up in a bookshelf. Nolan told Thorne that, like in 2001: A Space Odyssey, he wanted an incomprehensible yet explainable ending. And just like in Space Odyssey, where you needed director Stanley Kubrick's commentary to make sense of the conclusion, with Interstellar, you need to read Kip Thorne's book. Thorne outright states this in one of his lectures. At the edge of the singularity, Cooper is met by a four-dimensional tesseract, which from afar looks like a sphere. I'll repeat, over the past quarter century, we've learned that our universe is likely a brain within a multidimensional bulk. And theoretically, it's perfectly reasonable to assume that beings exist in the bulk who could, at the last moment, use a tesseract to save Cooper from the singularity. This is the scenario the director chose. Cooper doesn't end up in a bookshelf. He ends up in an artificially created device that allows him, as a three-dimensional being, to interact with four dimensions. Strictly speaking, using this device, Cooper could have appeared at any point in space-time, not just in his 10-year-old daughter's room. Cooper sees Murph because light rays from her are traveling from the past to the future. But Murph, in turn, cannot see Cooper because relative to her, he is in the future, and light rays cannot travel from the future to the past according to the laws of physics. But why does this scene look so surreal? How else could you depict a four-dimensional device that a three-dimensional Cooper can interact with while ensuring the audience in the theater doesn't break their brains? This is what a regular three-dimensional cube looks like, and this is what a four-dimensional cube looks like. The result is the tesseract. And this isn't just any hypercube, it's a complex hypercube. Even though this tesseract looks like an acid-induced fractal trip, it's actually meticulously designed. So meticulously that to clearly explain how it works, you'd need to film a separate, fairly dull 20-minute video filled with technical details. I want you to at least grasp the scale of the work involved. Let me read a short excerpt from the chapter on the tesseract. Since the speed of the section's movement is finite, the rooms are not synchronized. For example, if the section passes from one bedroom to the next in 1 second, then all bedrooms, numbered in blue, are offset from bedroom 0 by the amount of time shown in black. Specifically, bedroom 2 is 1 second ahead of bedroom 0. Bedroom 9 is 2 seconds ahead, and bedroom 8 is 4 seconds ahead. The time interval between adjacent bedrooms is approximately 1/10 of a second. To move forward in time as quickly as possible, Cooper must move diagonally across the hall in the direction of the combined vector of blue, green, and brown times along the purple dashed line. That's how far the creators went. Next, we see Cooper nudging the world line of the clock's second hand with his finger. These movements generate a gravitational force in the past, causing the clock hand to twitch, transmitting quantum data via Morse code. The tesseract preserves the motion of the clock hand within the bulk, so it repeats over and over again. There were many complaints about how Morse code could transmit so much data. How much data? The information only needs to contain the values of the unknown terms in the professor's equation. While in the tesseract, Cooper desperately tries to stop his past self, and these very attempts ultimately provoke his departure. This isn't exactly stated anywhere, but these frames demonstrate the so-called Novikov self-consistency principle. This principle resolves the paradoxes that arise from Einstein's equations and postulates the absolute futility of trying to change the past. Alright, the data transmission is clear. By manipulating gravity, which hypothetically isn't constrained by 3 dimensions, Cooper was able to send quantum data into the past. That's settled. But what about Cooper himself? Remember what I said at the very beginning, that space and time flow into a black hole? That after crossing the event horizon, no matter how fast you go, you will still end up in the singularity? And that escaping a black hole is the same as traveling back in time? That's all absolutely true for our 4-dimensional universe. But the bulk, the 5th dimension, does not belong to our universe. It is our universe, with all its black holes, that exist within the bulk. The distance from Gargantua to Earth, according to the script, is 10 billion light-years, if measured within our universe with its 3 dimensions. However, if measured within the bulk, Thorne's calculations reduce this distance to just 150 million kilometers. And again, this figure isn't just pulled out of thin air. The logic of these calculations is detailed in an entire complex chapter of the book. To understand that chapter, you need to first grasp the concept of the anti-de Sitter curvature. This scientific idea is schematically depicted on Professor Brand's board. To summarize, by moving through its 5-dimensional bulk, the 4-dimensional tesseract can safely and quickly deliver 3-dimensional Cooper from one edge of the universe to the other, bypassing Gargantua's tidal forces. I know how this sounds. Let me offer a simple analogy. Imagine an ant on a reed being sucked into a massive whirlpool of water. The flow of space and time pulls it towards certain doom. But if the ant is caught in a helium-filled balloon just at the right moment, the whirlpool's tidal forces are no longer a problem. Why? Because the whirlpool only pulls objects trapped in its 2-dimensional surface, while the helium balloon can move in 3 dimensions. The 3-dimensional balloon, with the 2-dimensional ant, can simply float upward. This is exactly what happens to Cooper, and the tesseract is pulled into the bulk, away from the singularity. So, all the science in the movie can be divided into 3 categories. Number 1. Scientific truths. To be called truth, scientific knowledge must be based on established physical laws and supported by sufficient observations. For example, gravitational lensing. The way Gargantua bends light is based on relativistic equations and matches scientific truth. That's exactly what it would look like in reality. Number 2. Reasonable assumptions. An example is the crop disease in Interstellar, which threatens human life on Earth. Cases where a plant disease spreads rapidly from one species to another, endangering human life, are unknown. However, we have no guarantee that this couldn't happen. The possibility of such contamination is a reasonable assumption. Number 3. Speculation. For example, when Cooper drops a coin and it sticks to a specific spot on the floor, that looks like complete nonsense. Why? Because in the entire history of physics, experimentalists measuring gravity have never recorded any gravitational anomalies on Earth. They've searched. Oh, they've searched. However, when physicists apply Einstein's theory of relativity to the bulk, and they have no reason not to, they note the possibility of gravitational anomalies caused by physical fields acting within the bulk. That's what speculation is, ideas accepted by at least some respected scientists. And how many times throughout history has speculation turned into reasonable assumptions, and then eventually into scientific truth? 10 years after its release, I can still say that Interstellar is the most scientifically grounded film in modern science fiction. I mean, seriously, what other movie can boast a companion book written by a Nobel Prize-winning physicist that comprehensively explains the events on screen from a scientific point of view? Thank you so much for watching. If you liked the video, please subscribe to the channel. Be sure to share your opinion in the comments.